Okay, in this next section we have optimization problems. You see these again in Calc 3. Basically, you'll have a formula you want to optimize, and then you'll also have a restraint formula. You use the restraint formula and the optimization formula, take the derivative, maximize it, and you'll have your solution to the issue. Okay, so the first kind of problem we'll look at is the area, maximizing area, and particular number 9. So this is from the Larson book. Find length and width of the rectangle that has given perimeter and maximum area. This out of the way. Find length and width of a rectangle with given perimeter and maximum area. Okay, the given perimeter is 80 meters. Okay, so this is our restriction. And the formula we want to optimize, of course, is the area formula. So maybe we need a little picture here. Here's our rectangle. Let's call the base x and the height y. So A is equal to x times y. Okay, so what you're going to do is use the restriction to simplify the formula you want to optimize into one variable, take the derivative, find the critical number, and that should be your max or min. Okay, okay, so the perimeter formula, you probably remember from basic geometry, 2 times width plus 2 times length equals p. In this case, that's 80. Okay. So from this fact that perimeter is 80, we get a restriction formula, and or a constraint formula, I guess we could call it. And then, of course, we have our optimization formula. Okay, so again, we use the constraint formula to simplify this formula. So how does that work? You solve for either x or y. So this should be y, sorry. So let's solve for y. I have 2x plus 2y equals 80. So 2y equals 80 minus 2x. And then divide everything by 2. So you get y equals 40 minus x. And then we take that and pop it back into the optimization formula. Right? So we want to optimize area, which now equals x times 40 minus x. Okay, so to take the derivative, we want to distribute the x, so 40x minus x squared. So the derivative of this will be 40 minus 2x. And set it equal to 0 for your critical number, and that usually turns out to be what you're looking for. Okay? So setting equal to 0 and solving, x is 20, and y then is 40 minus x, which is 20, so that's equal to 20. Okay? So there'll always be a question as to whether or not it's a max or a min. If you're real obsessive about this kind of thing, you can take the critical number and plot it and then do some test values in the derivative formula. Okay, so we'll have 40 minus 0, so it's positive, and then 40 minus 60, only negative, so it's increasing and then decreasing, and certainly we have a maximum at the critical number 20. So this will be our solution, which optimizes the area. So the length we'll say is 20 meters, and our width we'll say is also 20 meters. Okay. So it's pretty simple. The book is going to try to, make it complicated as possible. Let's look at another problem. So this is the, sorry, it's a matter of time before that breaks. Great. Okay, so the Norman window problem is what we want to look at next. It's page 263. And of course, now that's going to be a lot of fun for the rest of the lecture. It's just like in class, we have that light that goes on and off. Now we also have it here. It just makes sense. Things make sense like that. Okay, so here we are. There's like no way to keep it from falling, apparently. And of course, it's a 3 million degrees hot light bulb. Oh my God. Okay, great. So 21, we're trying to maximize the area of a Norman window, and it's constructed by adjoining a circular semicircle top to an ordinary regular window, and they give us a nice picture. And of course, now my camera is all out of whack. Okay, so they give us a nice picture here. Yeah, so Norman window is rectangular, and then on the top it'll have a semicircle. Okay, the dimension they give us is this bottom part is X, and then the side part here is Y. Okay. So the constraint is that the total perimeter is 16 feet. The restriction okay. So we need an equation for the perimeter, and then we need an equation for the area. So the perimeter then, the formula for that in terms of x's and y's is just going to be y, plus x plus y. So 2y's plus x, and then plus the circumference of the semicircle up here. The total circumference of the circle is 2 pi r, so it should be pi times the radius, and we need to note the radius here from here to here is just going to be half of x. Okay, so x over 2. So it'll be pi times, instead of 2 pi r, it's half the circumference. So 2 pi r over 2, so pi r, and r is x over 2. Okay. So this is then going to give us the constraint formula, 2y plus, and I don't know if you want to factor out the x times 1 plus pi over 2 equals 16. Okay, then the formula we want to optimize, of course, is the area of this thing. So the area of the rectangular part is just x times y. And then the area of this semicircular part is half the area of the circle. So 1/2 times pi r squared. So pi, and then r, again, is x over 2. And then we want to square that. Okay, so our area formula then, x times y plus x squared over 4 times 1/2 is x squared, pi x squared over 8. Okay, so we want to use the constraint formula to, again, minimize the area formula. So this is our constraint. Not minimize the formula, but we want to use the constraint formula to simplify the area formula. So put it into one variable and then take the derivative. So in order to do that, I need to solve this equation for one of the unknowns, and I'll just solve for y. That'll be a little easier. So 2y equals 16 minus x times 1 plus pi over 2. Divide everything by 2, and you get y is 8 minus x over 2 times 1 plus pi over 2. I'm just going to distribute that 1/2 through, and I'll have 1/2 plus pi over 4. Okay. So then, again, I'm simplifying the thing I want to optimize by putting the constraint into it. So I'm going to plug this formula into here. And so that'll give me for the area, A equals x times 8 minus x times 1/2 plus pi over 4. See, this is a simple problem, but they just made it a nightmare with all the constants. Anyways, plus pi x squared over 8. Okay. So I need to take the derivative of this thing. What is it as it sits? It's 8x minus x squared times 1/2. So we go x squared over 2 minus, x squared pi all over 4. And then plus pi x squared over 8. Okay, I want to simplify the heck out of this. So I have 8x minus x squared over 2, common denominator. So minus x squared, or pi x squared over 8. And then I'm going to factor out the x squared, so I'll have 8x minus x squared times this constant of 1/2 minus pi over 8. Okay, so we want to optimize it. In other words, take its derivative. Right? So a prime, working this thing, the derivative of the first one is just 8. And then the derivative of this, I mean, literally, this is just some constant. So you can kind of just take the derivative of this and have a constant floating about. So it's minus 2x times 1/2 minus pi over 8. We can distribute the 2. We're going to be setting it equal to 0 here. So 8 minus x times 2 minus pi over 4. And then we want to solve for x. So we'll have x times 2 minus pi over 4. Let's get a common denominator on that guy too. So this is 8/4 minus pi/4. So 8 minus pi all over 4 equals 8. Multiply by reciprocals, and we should have our one of our solutions, 32 all over 8 minus pi. Barring any mistakes, let's see if I made any mistakes. Seems like I did. I'm sort of looking at it. Let's see. Going back to the original expression, let's make sure this guy's okay. Where are you? Here. Yeah, there's a mistake there. This should be plus when I factored it out. Sorry. 1/2 plus pi over 8. 1/2 plus pi over 8. So 8 plus pi over 4. And then 8 plus pi all over 4. So this should be 32 over 8 plus pi. And even there's a mistake in there, right? Oh, right here. I found my common denominator. I screwed that up. multiplied top and bottom by 4. So this would be 1, and then, yeah, so this should be 4. I totally apologize, I butchered this one. See, it's annoying. It's not hard, it's just there's little issues going on here. So this one is going to be 4 plus pi, and then down here this is 4 in the denominator, 32 over 4 plus pi. Okay, then that's the correct answer. Either zip back then and find the y value. So y is equal to 8 minus 32 all over 4 plus pi. Let's find a common denominator here. Hopefully I don't screw this up. So 2 plus pi over 4. I think. Let's see. Pi over 4 minus x is 32 over, I think. Then let's see what this is. 8 minus 4 goes into 32 8 times, and then we can distribute. We get 16 plus 8 pi all over 4 plus pi. Then I want a common denominator here. So multiply top and bottom by 4 plus pi. So you get 32 plus 8 pi minus 16 minus 8 pi all over 4 plus pi. And then this will be 32 minus 16 is 16. Yeah, it's just 16 all over 4 plus pi. Okay. So really this should be thought of in that way. Okay. So our solutions then are right here for our optimization. Not pretty at all, but there they are. These are in feet. All right, so I butchered that one. Let's look at 25. This time the constraint is semicircle. So find the length and width of the rectangle to maximize the area of the rectangle. Given that the rectangle is circumscribed in a semicircle of radius r. And they give you a picture, so let me draw the picture first. Semicircle radius 5. 5. Okay. So the formula of this guy here then, the upper half of the semicircle, y equals square root of 25 minus x squared. That should be your constraint formula. Okay? And we're trying to put a rectangle in here somewhere. And we're trying to maximize that rectangle so its area is maximized. Okay, so the bottom dimension, if we were to take a look at this length, is going to be x plus this other x direction. So it would be 2x. Okay. The height then is this y value, which is based off of this right here. So the formula for area, as usual, is base times the height, I guess, or length times width, however you want to do it. In this particular circumstance, the area equals the base, which is 2x times y. Okay. So this is the formula we want to optimize. The constraint formula, of course, is y equals square root of 25 minus x squared. So what you're going to do is plop this guy into the area formula. So the area is going to now be 2x times the square root of 25 minus x squared. And then we got a little bit of work to do, right? So take its derivative. So I'll leave 2x alone first, just get this derivative out of the way, times power rule 1/2 times 25 minus x squared to the negative 1/2 times the derivative of the guts, which is negative 2x. And then plus, now we're going to leave this part alone, take the derivative of this. So you'll have 2 times the square root of 25 minus x squared. Right? Want to clean this up significantly. So 2 times 1/2 is just 1, and then we have a negative 2x. So x times negative 2x is negative 2x squared all over the square root of 25 minus x squared. And then plus 2 times the square root of 25 minus x squared. Okay. I'm going to set it equal to 0, find a common denominator here. So on the second term, we can multiply top and bottom by 25 minus x squared. Okay. So we'll have 0 equals negative 2x squared plus 2 times 25 minus x squared, which will be 50, minus 2x squared all over the square root of 25 minus x squared. Okay. So we'll end up with 0 equaling negative 4x squared plus 50 all over square root of 25 minus x squared. The undefined points this time are not going to give you rectangles, so you don't have to worry about those as critical numbers. They are critical numbers, but note they would be plus and minus 5 for your x value. So if it was plus 5, the y value would be 0, so you wouldn't have a rectangle at all, you just have a straight line. Okay, so we can exclude those from our conclusions and just set the numerator equal to 0. So you have 4x squared equals 50, and then x squared, of course, equals 25 halves. And then take square root property on both sides. X equals plus or minus 5 over root 2, or if you'd rather 5 root 2 over 2. Obviously, we're going to exclude the negative answer. We just want in the x direction, the positive x direction. So we want this number, whatever the x value is there. Now we want to find our answer. The y value, in this case, square root of 25 minus this thing squared, which is 25 halves. So you end up with 25 minus 25 halves is 25 halves. And again, you're going to get 5 root 2 over 2. But it's not 5 root 2 over 2 by 5 root 2 over 2. Remember, this dimension here is actually 2 times the base. So our answer will be 2 times this. In other words, 5 root 2 by the height value here, 5 root 2 over 2. Units, whatever the units. I think the units are feet. Okay, so that's pretty much how these work. You find a constraint formula, you find an optimization formula, and then you use a constraint formula to simplify your optimization formula. And then you take the derivative of the optimization formula, find the critical number, and usually that's going to be your solution. Okay. Let's look at page am I on? Let's take a look-see at distance problems. So we're trying to minimize or optimize some sort of distance. And of course, the distance formula, d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay. Right. Typically, when we work with these, we're going to work with the square of this thing, so we have to worry about the square root. Whatever value will maximize the guts of the square root will simultaneously maximize the square root of that thing. Okay. So generally, then we're going to work with maximizing or optimizing the formula, and I'll just use the letter D again for sake of sanity. No, let's use a different. Let's say f of x. Okay. we'll optimize f of x equals x 2 minus x1 squared plus y2 minus y1 squared. Okay, so if you optimize this, you've effectively optimized this, is what we're trying to say. Okay, so find the point on the graph closest to the given point. Okay. So the formula we're optimizing is the distance, the square of the distance formula, and then our constraint formula becomes the graph. Okay, so we can even take a look at the graph. It's square root, so at 1, it's 1, 2, 3, 4. You have 2. Okay. And we want the y value, or rather the point on this graph that's closest to this point here. It's not immediately obvious, you know, maybe that point is over here as opposed to right here. Maybe this length is shorter than this length, or maybe this length is a little shorter, I don't know. Okay, okay, so I go to my distance formula that I'm trying to optimize. So f of x, we'll say, is x minus, and we're going to plug in this point. Okay, so x minus 4 squared plus y minus 0 squared. So this is the formula we want to optimize. The constraint then allows us to simplify that formula. And the constraint is this g of x equals square root of x. Okay. So what we'll do then is just plop this into here, and we should be good to go. So here's our new formula to optimize f of x is x minus 4 squared plus y squared, which is now square root of x squared. So our f of x will be x minus 4 squared plus x. And then we can take its derivative. F prime of x is power rule 2 times x minus 4 plus 1, which is 2x minus 8 plus 1, which is minus 7. And so set it equal to 0. 0 equals 2x minus 7. So 2x is 7. And then finally, x is 7 halves. Okay. So it's 3.5, comma, whatever this value is, that will minimize that distance. Which is pretty crazy, because just visually looking at it, it seems like this would be the shortest distance, but it's not. Okay, so anyways, get the y coordinate. So g of 7 halves is equal to the square root of 7 halves, whatever that is. And so our point on the graph, which minimizes the distance, 7 halves, comma, square root of 7 halves, or if you prefer, square root 14 halves for our solution. Okay. Let's take a look at an engineering sort of application on beam strength. So this is now, I believe, section 4 in my notes. Beam strength, problem 37. We are looking head-on at a log. It's on page 264 in the Larson. And it says, the wooden beam has a rectangular cross-section of height h and width w, and they show us a figure. So it's a cross-section of a piece of wood, a log, and they have a little box drawn in here where this is w and this is h, and then the strength S of the beam is directly proportional to the width and the square of the height. So we'll say the strength S is proportional, directly proportional, so you're multiplying by a constant, times the width times the square of the height. Okay? So directly proportional is just multiply. Inversely proportional would be a different story. Okay. So what else do we have? The strength of the beam is directly proportional to the width and the square of the height. Okay, not the square root, but the square. What are the dimensions of the strongest beam that can be cut from a round log of diameter 20 inches? Okay, so the diameter here, you could go from corner to corner, and note this is 20 inches. And it even tells you the formula. It gives you a hint and tells you this formula, so you don't even have to bother. Okay, so from the picture, I can reduce the number of variables. This becomes your restriction. This picture is a restriction, basically. So we want to optimize this thing. And we're restricted by the log picture. In particular, we can relate W and H using Pythagorean theorem. So basically, W squared plus H squared is equal to 20 squared. And then solve for H squared and reduce the number of variables in the optimization formula. So H squared is equal to 20 squared minus W squared. And I'm going to resist the desire to solve for H, okay? Because H squared is its natural form in the equation anyways. So and now we use this to simplify the number of variables, reduce the number of variables. So our strength formula now, some constant K times W times H squared, which is now 20 squared minus W squared. Okay. So I want to take the derivative of this. So S prime is equal to, and that might be helpful to say this is 20 squared K W minus KW cubed. Okay, so the derivative of this with respect to W then is 20 squared K and then minus 3KW squared, just using a power rule. Bring down the 3, subtract the old exponent by 1. So minus 3KW squared. Set it equal to 0. So you have 0 equals, I don't know, just whatever we had there, 20 squared K minus 3KW squared. Let's move the W squared to the other side. So 3KW squared equals 20 squared K. And the constant turns out not to matter. Okay, so it will divide out. So you have W squared equals 20 squared all over 3. Take the square root of both sides. We don't care about the negative root. We just want the positive. Square root of 20 squared is 20 all over the square root of 3. So if you'd rather 20 root 3 all over 3 for the width. I'm not sure what the dimensions are. Inches. Okay. Then we need to figure out our H value. So H squared is equal to 20 squared minus W squared. W squared is 20 squared over 3. Common denominator, this will turn into 2 times 20 squared all over 3. Take the square root of both sides and you get H equals 20 times the square root of 6 all over 3. And that's it. So inches, of course. Oops, sorry, I ran off the page there for you. So that'll be that. Okay.